Hello friends, today in this video we're going to wrap up chapter 13. That's right, we're going to finish our discussion of gas laws and we're going to detail how you can take a chemical equation based on gases and use it for calculations in stoichiometry. Yeah, stoichiometry, I know, but really it's not going to be that bad, okay? Trust me, stick around. Now, we've already seen how these chemical equations can be used to report on moles or molecules, right? As in this one, where we have the reaction between hydrogen gas and oxygen gas to produce water vapor. In this equation, we can see that 2 molecules of hydrogen can react with 1 molecule of oxygen to produce 2 molecules of water vapor. Or 2 moles of hydrogen, right, can react with 1 mole of oxygen to produce 2 moles of water. But here's the cool thing about gases. We can also use it to describe volumes because of Avogadro's principle, which tells us that equal volumes of gases at the same temperature and pressure have the same amount of particles. So, because of that, we can talk in terms of volumes of gas in this case. In other words, 2 volumes of hydrogen combined with 1 volume of oxygen yield 2 volumes of water vapor. That volume could be in liters or cubic meters, whatever, as long as you're consistent throughout the equation. Just like any stoichiometry problem, we have to start with a balanced equation. But as long as we have the mole ratios and the volume of one of the reactants or products, we can find all the rest pretty easily. How about this reaction between propane and oxygen? We have 1 volume of propane, you see, and 5 volumes of oxygen, which yields for us 3 volumes of carbon dioxide and 4 volumes of water. So let's say we're talking in liters. 1 liter of propane combined with 5 liters of oxygen gas will yield for us 3 liters of carbon dioxide and 4 liters of water vapor. So let's say we had 4 liters of propane. How many liters of oxygen gas will we need for a complete reaction? We start with our 4 liters of propane, and then we use a conversion factor with the mole ratio between propane and oxygen, with the oxygen on top, of course. The units for propane cancel, and we're left with 4 times 5, 20 liters of oxygen. That wasn't so bad, was it? You'll notice we didn't say anything about temperature or pressure in this calculation, and that's because they're not really needed. After it's all said and done and all the mixing occurs, these gases will all be at the same temperature and pressure. And if there's any changes to the temperature or pressure, it's going to affect all the gases, not just one. That's why we didn't have to worry about temperature and pressure in this case. The previous problem was an example of a volume-volume problem. Let's do a volume-mass problem. In other words, starting with the volume of one gas and ending up with the mass of another. In this case, we'll involve the ideal gas law in the process. Let me show you how. Let's say we have the reaction between nitrogen and hydrogen to produce ammonia. If we start with 10 liters of nitrogen gas with plenty of hydrogen to go around, and the pressure in the reaction vessel is 3 atmospheres with a temperature of 298 Kelvin, how many grams of ammonia will we produce? Let's start first by determining how many liters of ammonia will be produced from that 10 liters of nitrogen. According to our equation, for every 1 volume of nitrogen, we'll produce 2 volumes of ammonia. So, if we have 10 liters of nitrogen, that means we'll produce 20 liters of ammonia. You see that? I used the mole ratio to determine that. Now again, that was a simple calculation that didn't involve temperature or pressure for us. But if we want to figure out how many moles of ammonia we have, we're going to need to use the ideal gas law for that, since we're not at standard temperature and pressure. Here, of course, is our ideal gas law, PV equals nRT. We're going to solve for the number of moles, which means we need to rearrange this. So, if we divide both sides by R and T, we'll get number of moles is equal to PV divided by RT. And now what we have to do is fill in. We said that we have 3 atmospheres of pressure. The result of our reaction was 20 liters of ammonia. Our R value is going to be 0.08206 since we're using atmospheres. And we have a temperature of 298 Kelvin. When we do the math, we come up with an answer of 2.45 moles of ammonia. There's only one more thing we need to do, and that's convert this into grams. Remember, when we're going from Molopolis to Gramsberg, We multiply by the molar mass. We use the periodic table to determine the molar mass of ammonia. That is 17 grams per mole. Multiplying 2.45 times 17 gives us an answer of 41.7 grams of ammonia. So when we start with 10 liters of nitrogen gas in this reaction, we end up with 41.7 grams of ammonia. Okay, here's a homework problem for you. Let's say we have this reaction, the reaction between hydrogen sulfide gas and oxygen to produce water vapor and sulfur. If we start with 6.5 liters of hydrogen sulfide gas at a pressure of 2 atmospheres and a temperature of 290 Kelvin, how many grams of H2O will be produced in the process? Okay, starting with liters, ending with grams. You can put your answers in the LMS. That's all we're doing for this video. Today we talked about gas stoichiometry, how chemical equations will relate volumes of one gas to another for us, and from that we can do stoichiometric calculations from volume to volume or even volume to mass. I hope it's been helpful to you, but let me know if I can assist you in any other way. In our next chapter, we'll begin talking about solutions. So until then, God bless.